In this tutorial, I'll show you what shadow maps are and how you can use them to add shadows to your scenes with directional lights. So as you may know, shadows are simply the absence of light. And since the light we have implemented so far does not bounce from one surface to another, it will only reach the surfaces that are in its direct path. That means that if we look from the perspective of the light, the image we'll see will contain all the surfaces that are in light. So when we go over our usual fragment shader, we can shift our perspective to the perspective of the light to check if the fragment we're currently on is in light or not. How do we do that? Well, using the perspective of the light, we can create a depth map called the shadow map, which holds all surfaces that are in light. When switching to the light's perspective, we can check the depth of the current fragment we're on against the depth present on the shadow map at those coordinates. If the depth of the shadow map is smaller than the depth of the fragment, then that means that the fragment is behind the surface that is in light, and so we'll get no light. Thus, we consider it to be in shadow. If it's not smaller, then we consider the fragment to be in light. And that's it for the theory. Now let's implement this. The first thing we'll want to do is to create a frame buffer for the shadow map and a texture to store it in. Make sure the texture holds depth and not color, and also make sure to clamp the texture to the borders with a white color. Since the shadow map can only look at one area, anything outside that area will have a depth value of 0 and thus always pass the shadow test. We instead want everything outside the shadow map to have a value of 1 so that no mesh can be in shadow. Since we won't be using the color buffer of the frame buffer, we want to specify this using GL draw buffer GL none and GL read buffer GL none. Now that we have the frame buffer, we next want to specify the matrices we'll use for the perspective of the light. Since the rays of directional lights are parallel to one another, we want to use an orthogonal projection as opposed to a perspective projection which warps these parallel lines. Now the sizes of this projection will depend from scene to scene, but as a general rule of thumb, you want to start with a large size and narrow down to fit the scene. If the size is too big, you will still get shadows, but of a lower quality. The better fit it is to your scene, the better the shadows will look. This is of course due to the limited resolution of the texture. Now we'll want to look at matrix, so to say, from the position of the light. The thing about directional lights though is that they are infinitely far away. So we'll just have to settle for a position along the ray that goes through the origin or any other point that will keep the rays parallel to the center of the view. In this case, I am defining my directional light using my light pose vector, so I will use that for the position, but I'll multiply it so that it is far enough to encapsulate the things I want to have shadows. Again, keep in mind that the closer it is to your scene, the better. And the last step to get the transformation matrix for the light is to multiply the orthogonal projection matrix with the light view matrix. Now we'll want to create two new shaders for the rendering of the shadow map. In the Vertex shader, we'll simply multiply the light transformation matrix by the model matrix and the vertex position. As for the Fragment shader, we'll simply leave it blank since we don't care about the color buffer and the depth gets registered automatically. After that, we want to create our shader program and export our light projection matrix to the shadow map shader. Now we want to get that depth on the shadow map, so we'll want to enable the depth buffer and draw our scene from the perspective of the light. Keep in mind you'll need a different viewport from the usual to accommodate for the size of the shadow map. Also don't forget to clear the depth buffer of the shadow map FBO and then bind the default frame buffer at the end. At this point of the video, you should try and render your shadow map to a rectangle on the screen so that you can make sure nothing went wrong. If all went well, you should see something like this. Now that we have our shadow map, we want to switch back to our default viewport and draw the scene like we would normally draw it, except we'll send the light projection matrix to our default shader and bind our shadow map. I will bind it on the third unit, since the first two are taken by the diffuse and specular maps. Now in our vertex shader, we want to take in the light projection matrix and output the frag position light, which is just the current position, multiplied by the light projection matrix. Now for the fragment shader, we want to take in this matrix as well as the shadow map. Now we want to create a float where we can store the value of our shadow. 0 will mean that there is no shadow and 1 will mean that the shadow is at its greatest. Now we want to do a perspective division on the frag position light so we get it into clip space. We'll only calculate the shadow if the Z value is smaller than 1, aka if we're inside the frustrum of the orthographic projection. Then we want to get it from the range -1, 1 to the range 0, 1, so it is in the same range as the depth map. After that, we simply check if the current diff is bigger than the closest diff, and if it is, we set the shadow equal to 1, otherwise we leave it as it is at 0. All that's left to do is to multiply the diffuse and specular lighting by 1 minus the shadow. That way, when the shadow is 1, the diffuse and specular will be 0, and when the shadow is 0, they will be whatever they were normally. If you run your program, you should get something like this. Not the prettiest shadows you've seen, probably. We get all of these artifacts because the shadow map has a finite resolution, and so multiple fragments use the same pixel on a shadow map. The problem arises when the shadow map was sampled at an angle with the surface, and so parts of the pixels cover areas under the surface. But since the fragment shader has a much higher resolution, so to say, it calculates fragments whose shadow map pixel can be above them, and at the same time fragments whose same shadow map pixel can be beneath them, resulting in this alternating pattern. So to fix this, we simply need to push down the shadow map by a certain bias. Now this should look much better. The problem is that the higher your bias is, the more your shadows will be offset. To prevent this as much as possible, a better solution would be to have a higher bias when the angle between the normal of the surface and the light is greater, and a smaller bias when the angle is small. You can achieve something like that using this formula, just keep in mind you will still need to tinker with the max and min values. Now, one more thing we can do to make the shadows look nicer is to soften them out a bit. To do that, we can simply loop over the surrounding pixels of the shadow map and check to see if they are in shade or not. If they are, we add 1 to the shadow value. Then at the end of the looping, we divide the shadow by the amount of samples we took. And now we have nice soft shadows. Before I go, I would like to let you know I now have a Discord server where you can drop by for some help or just to say hello. Besides that, I also have a Patreon now, speaking of which, I would like to thank my first Patreon, Martin, and also Kyle and Dreamplay. As always, the source code and all sources and resources used are in the description. Bye.